I'm going to show you how to use ARIMA forecasting for a time series so that we can forecast the number of cases of COVID-19. Firstly, this is the site where we got our data from, and this is the number of cases and deaths by US county and state. I'll put a link in the description so you can access this data set. So in R, I'm going to do all of my data engineering. So I wrote this script. We have our input directory, output directory. I specify that at the top. So you could actually use this entire script if you wanted to. Literally all you'd need to modify is the input and output directory. It's very reusable code. This line we import our data. With these 4 lines we're just importing libraries. Now here I make a copy of the data, this new data set, I'm calling it data 0. You shouldn't make any changes to the original data, because if you do that you might mess something up and then you have to import it again. And sometimes importing takes a long time, so instead I just make a copy of it and I make all of the modifications to the copy. So I'm making a copy of the data, and this is a very powerful function called a ddply, because it's equivalent to Python group by. We actually want to summarize this data nationwide, so we're going to summarize it only by date. In order to build an ARIMA model, there are 3 parameters that you can change. You can change parameters P, D, and Q. There are a lot of resources online of how you can optimize P, D, and Q, and I'll be honest, it's a kind of a complex process. Sometimes the data is going to be ambiguous, sometimes it's not obvious what P, D, and Q are, and so I thought, why go through all of the theory to determine these parameters? Because in data science, it's a lot more common to just do a grid search. So I did that instead. I created a grid search where I searched through several different values of P, D, and Q, and I let the program tell me which values are optimal. So this grid search, I didn't use a fancy function for it, although you can use caret to do grid searches in R, but I didn't know if that would work for time series. So instead I just did 3 nested for loops. So we're going to search for these values of P, these values of D, and these values of Q. And we're going to build many different ARIMA models. If you went with the traditional route of evaluating PACF and ACF graphs, sometimes the optimal solution isn't obvious from a graph. Here I use a try function because sometimes the model will return an error, and I don't want the console to halt or terminate whenever there's an error, so you can use a try function to bypass errors. And I'm going to compare all of these models by MSE. Alright, so let's take a look at the results. So that ran really fast, so we might need a much higher value for P. Yep, we still need a higher value for P. So it looks like we may have finally converged again. So in this case AR can only be a maximum value of 10 in our Gretel model. Alright, so this time we converged again, limiting P to be a maximum of 10. To build my forecast, I'm going to use Gretel. Now notice that in R I did modify this data a bit. For example, I applied ddply so we could group all of the observations by date. So we actually need to export this result here, so I'm going to run this line, and we just exported a modified data frame, and that's what we're going to open in Gretel. I'm breezing through this a little bit, but if you search YouTube, you can find some excellent tutorial videos on Gretel, so I'll put a link in the description to one of those videos. We're going to forecast 50 days out, and we also want first differences, and that's because we also want to look at cases by day. And now we're going to export this data, and Tableau, if it detects text values, it will assume that you passed in something that was a character value instead of numeric. These are not supposed to be character values, they should be numeric. So we're going to just delete all of these fields so Tableau doesn't misinterpret the data. And now we're just going to use Tableau to visualize the time series and our forecasts as well for comparison. Actually, I was skeptical at first, but this is actually a really good forecast compared to all of the other forecasts I made. And the only way we got it to perform this well was by using the maximum value of P, which accounts for those oscillations. Now, you can rightfully say that's probably overfitting, so this time we're going to look at the cumulative number of cases, and we're going to look at the long-term projections. Even though we overfit, I think it's going to give us more credible long-term forecast than anything else. So I'm actually very pleased with this result, and I could expand this to try to predict the total number of cases worldwide. Now, in order to be credible, I should tell you that forecasts, generally speaking, don't work except for when one of two conditions are met. Either one, you're predicting a variable in a simple system. A simple system meaning there are not unfathomably many external variables impinging in ways that you can't comprehend, which would be the case for the stock market, or the temperature in the atmosphere, or CO2, or population, or the spread of a disease. The second condition is that the data is just very stable and predictable, and it might have some seasonal variance, but other than that, it's stable and it's not changing very rapidly. But if you're actually looking at real-world erratic data, there's no way to actually forecast it in the long term. There's no time series that predicted the stock market crash of 2008. Time series did not predict the Iraq War. The time series didn't predict the spread of COVID-19. So time series just don't account for anomalous events. Time series never account for black swan events. They're not a magic trick. Time series really just basically say, assuming that the data continues to trend, as I've currently seen it trend, here's what the future values would be. Now that assumption is fundamentally wrong if you're dealing with a real-world complex system. In real-world complex systems, the only thing of which you can be certain is that the future data will not be the same as the past data. Some new anomalies are going to occur to throw off your predictions. And that might not be true for short-term forecasts, but the further you project in time, the more likely your projections are going to be wrong. That's why you have confidence intervals, and the confidence intervals explode the further out that you project in time. Now, when the media report long-term projections, like in the year 2050, this is what the sea level will be, this is what the temperature will be, I can promise you unequivocally that the scientists who are making those forecasts know that those are not reliable forecasts. If the scientists are smart, and I'm pretty sure they are, they know that those projections are implausible. It would be a miracle if any of those projections were accurate. That's how implausible those long-term projections actually are in a complex system. But the media report it as if those projections are reliable. They're not just unreliable, they're pretty much guaranteed to be wrong. That's very misleading because the public, they're not familiar enough with data science to know that they're hearing uncredible claims. So when the media report those long-term projections, I'm not sure if they don't know any better or they know better and they're just happy to use whatever projections favor their confirmation biases. And again, I'm not politicizing this. Data is manipulated by every ideology. But the moral of the story is, however good these results look, bear in mind, I basically hugged the training data. And I do want to stress, if you hug the training data, that absolutely does not predict future data. Hugging observed data is something that you can do with any model, right? If you wanted to, you could program a Loess curve to just hug this data and smooth it out. That does not make it predictive. But it's an educated guess, assuming things trend as they've trended in the past, which of course is not the case. Basically, time series generally don't work, but they give you the best educated guess that you could have. So it's really better to rely on them than to not rely on anything. And an interesting property about this curve is that you can see that COVID-19 cases are still going to trickle in for a long time. So they're going to trickle in for maybe another 3 months. Alright, well that's all I've got. If you have any questions about the methodology or the source code or interpretation, let me know.